Hello students, so today we are going to start the next topic, and that is instrumentation amplifier. Basically, instrumentation amplifier is used in measurement system for signal conditioning. Instrumentation amplifier consists of three operational amplifiers. So I am just going to start with the little basics of operational amplifier so that you are able to understand your instrumentation amplifier better. So firstly, we come on to the main symbol of the operational amplifier. It consists of a triangle having one negative terminal and a positive terminal and a output. So that means if we are going to provide it a input at the positive terminal, we are going to get amplified output and in same phase as the input. But if we are going to provide it output at the inverting terminal, this is called your non-inverting terminal because you are giving the input at the positive terminal. So this is non-inverting, and the negative terminal is called inverting. Why? Because when you apply the input at the inverting terminal, what you get at the output is 180-degree phase shift. So that is why it is called your inverting terminal. So yeah, now we come on to, this is your plus VCC and this is your minus VEE. So basically what is there inside this operational amplifier? Because all the defects that we are going to talk about, that what are the problems in the operational amplifier, comes from the difference in the structure of these two transistors, because operational amplifier consists of two transistors that are connected in the differential arrangement. So these both are connected here, not VEE, but we can say here not ground. So here we are going to give it minus VEE with a resistor in between, and here we are going to provide it VCC. Here we are going to provide it with input 1. Here it is input 2. While we say that this is 1, this is 2, so you can just correlate it with this is number 2 and this is number 1. When we are applying inputs at the operational amplifier, basically we are applying the input at the base of your transistor. Here you can see we are applying the input to the base of the transistor, and these two transistors provide us with the output. This is the output from where we get it. Let's say this is number 3 and this is number 4. So here, from here you get the output. Now basically when we say that we require two transistors, op-amp is consisting of two transistors, these two transistors should be having same configuration, same doping and same everything. Otherwise there can be some defects in the operational amplifier that we are going to study a little bit later. So let's first study about the two basic outputs from your inverting and non-inverting. So before this, there are some properties of operational amplifier. The very first thing that we take is the open loop gain should be infinite. Second is the input impedance should be infinite. Then we talk about bandwidth, that should be infinite. And what we require 0 is output impedance should be equal to 0. And next is noise generation should be 0. So these two things we don't require, but these we require in a very high output. So ideally we say that the input impedance should be infinite, but it is not. It is in mega ohms, while output impedance is not 0 and it is in ohms. It is around 100 ohms to that. So basically when we say that input impedance should be infinity and output impedance should be 0, with this configuration, the loading effects are minimized on any system. So again, this topic we are going to take a little bit later, that what are loading effects on any measurement system. So now taking this thing into account, we are going to derive the equations for your inverting and non-inverting amplifier. So firstly, we come on to your inverting amplifier. So basically, when you are providing the input to this is in differential mode. This is negative, this is positive, this is V naught, and this is your E in. This is your resistor R1, and let's say this is your feedback resistor, because always the negative feedback is used in operational amplifier. Now we have grounded because we are using the inverting mode, so that means the input E in has been applied onto the negative terminal. So now we have studied that the input impedance is very high. So that means if this is my current I1, and let's say this is my current I2, and this is my I0 current. So if input impedance is very high, then no current is going to go in your terminal, this one. Let's say this is terminal 1. So that means I0 will be equal to 0. And your I1 will be equal to I2. So now we have to see that what will be the value of your I1 and I2. So because E in has been applied on the terminal 1, so that means the value of I1 will be what we are giving here divided by the resistance of that terminal, because we are following Ohm's law that says it is equal to V upon R. Similarly, when we talk about your I2, because your this V naught has been fed back from here, so that means it will be equal to V naught upon RF. So equating these two in your equation, this will give me E in upon R1 will be equal to V naught upon RF. From here you can see that V naught upon E in will be equal to minus RF upon R1. So basically this is the equation for your inverting amplifier. Further we can say that V naught output voltage will be A times the input voltage. And mind it, this gain is very high in your operational amplifier. It is of the order of 10 raised to the power of 5 to 10 raised to the power of 6 and so much. So a very small input that is given here, let's say in millivolts. Millivolts means into 10 raised to the power of minus 3. So still you are going to get a very high voltage at the output. So this is why operational amplifier is used in measurement systems. So now we come on to the output equation of your non-inverting amplifier. The last equation is to be remembered. So that means now, because this is non-inverting mode, we are going to apply the input at the non-inverting terminal, that is the positive terminal. So this is my positive terminal. This is my V in now. This is my positive. This is my negative, and I have grounded my this thing. This is my R in, let's say, and this is my RF. So now we have got this as your V2 and this as your V1. From here you can see that V1 is nothing but it is equal to V in. So what about your V2? When we talk about your V2, it will be, because no current is coming here, so you have to apply the voltage divider rule here based on your E0. So total voltage multiplied the resistance across which we require the voltage divided by sum of the two resistances, that is Rn and Rf. So now we know that the output E0 is equal to A into, if there is a single input, then it is fine. You have to write A into whatever is coming inside. But now you have got some voltage over here because this is the feedback. Because of the feedback, some voltage will be here also. Like we have just seen that V2 value is here. So now it will be the differential value of the two, that is the difference between the two values. So it will be equal to, now putting the values, v1 is equals to v in minus whatever we have just got, that is e naught rn divided by rn plus rf. So now because this is also e naught and this is also e naught, so we have to combine these two terms. So that means I have to take my that term there, e naught plus a into e naught into rn divided by rn plus rf equals to a into v in. So now taking e naught common from your left hand side, taking your this e naught common and taking the LCM, so it will be rn plus rf plus arn divided by rn plus rf. So this gives me a into vn. So now taking my this whole thing towards that side, so this is going to give me a naught equals to a into vn rn plus rf, this is rf, so divided by rn plus rf plus a into rn. Now I already told you that the value of this a is very high, so if it is 10 raised to power 5 into rn, so this value will no doubt will be very much as compared to rn plus rf. So neglecting this whole term as compared to this, because this is very much. So even if it is 100 ohms, so 100 added to 10 raised to power 5 doesn't make much difference. So neglecting this term, I will be getting a into v in rn plus rf divided by a into rn. So now your a and a cancels out, and now you have got v in multiplied by rn divided by rn will be 1, and here it will be rf upon rn. So here you can see that in the case of your non-inverting amplifier, the output voltage is 1 plus rf upon rn into vn. So the gain here is different from the one we have discussed. Why? Because that was only minus rf upon rn. So this is the main difference between the output of inverting and non-inverting amplifier. So lastly, we come on to the voltage follower. So in voltage follower, you have to just keep in mind that what we are going to do in the voltage follower is we have to make our this thing 1. My this feedback resistor will be equal to 1 only. So the configuration will be equal to this Rn will be there, and this will be equal to, this is my E naught, and this is my V in that we have just given. This is my Rn, and now my this RF resistor, we have made it equal to 1 for the voltage follower. This is voltage follower, as well as the term buffer is used. Why? We will just discuss right now. So now in your this equation that we just derived, you can just put your this RF equals to 1. As soon as you have made RF equal to 1, what you have, E naught is going to follow your V in. Whatever you are giving at the input, the output will be the same as that of the input. So that means what we are getting is voltage is being followed as you are getting the output, so is the input coming. So the main advantage of using your voltage follower or buffer is that your voltage at high impedance is transferred to the voltage at low impedance, and that is why it is used as a buffer stage in the measurement system, so that to provide your this thing to the measurement system. So now we come on to your finally instrumentation amplifier. because instrumentation amplifier uses your operational amplifier. So the main thing about instrumentation amplifier that you should know, I'm just going to summarize the points here. So basically, when we talk about instrumentation amplifier, the very first thing is that it is a closed loop dedicated differential amplifier with a very high input impedance. So this thing is very much required when we have to measure as low voltages as that provided by your thermocouple or your piezoelectric transducer, because the input is very low magnitude, and so that is why we require a instrumentation amplifier with very high input impedance, as well as where the gain can be precisely set by a resistor. So it is very easy to set the gain of that particular amplifier by only moving the value of the resistor. High common mode rejection ratio, this we are going to discuss a little bit later. Common mode rejection ratio of this amplifier can recover even small signals buried noise. That means even if there is a small signal that is of our importance, that we care about, and there is a lot of noise in this particular signal, still your this amplifier can recover your this particular signal from the noise. Why? Because of the common mode rejection ratio being very high of this amplifier. Now it consists of two stages. The very first stage consists of two operational amplifiers. It offers high input impedance to both input signal, because we are providing it two input signals, and so it provides the high input impedance to them, as well as it is providing us with that resistor with which we are going to vary the gain. So firstly, we are going to discuss over this thing, but still what is there in the second stage is a single amplifier that takes the differential input. So this is the differential amplifier with output, negative feedback, and ground terminals. Output terminal is there in your second stage, then there is a negative feedback being used here, and then there is a ground here. So now we are going to first concentrate on the first stage of the instrumentation amplifier. So basically, when we talk about the first stage consists of two matched operational amplifier. Now this matching is, as I told you, that the transistor matching, as we discussed about a single operational amplifier, is very much required so that the errors don't come, like drift and offset don't come into the measurement system. Similarly, when we talk about two matched op amps, that means all the configurations are same of those both op amps, means same number of the op amp has been used. Now V1 and V2 are applied to, here you can see that they have been both applied to the positive terminal of your this operational amplifier, and it has been made as a voltage follower to get high input impedance. Now we come on to your this output of first stage is connected using two equal resistor of value R and the third resistor of value RG. Your this RG resistor is going to provide you to set the gain of the instrumentation amplifier. With by varying RG, you can set the gain. And now we are going to discuss that how we can change the gain. So now we are going to go for the derivation. So now this is our first stage, and let's say the voltage here is VA and the voltage here is VB. Now the current through RG will be equal to your this IG will be equal to, let's say this is IG right now for now. IG will be equal to Ohm's law, VA minus VB divided by RG. But if you just see that your this VA will be at the same potential as that of V1 and VB will be at the same potential as that of V2. So it will be equal to V1 minus V2 upon RG. But my this current I is also flowing in your R, in your this R as well. So that means if we are going to check out that what is the value of the current in your this arm, so it will be equal to your I will be equal to the voltage drops here, that is V01 minus V02 divided by the sum of all the resistors So that means now over this and this both should be equal. So equating both of them, what we are going to get is V1 minus V2 upon Rg will be equal to V01 minus V02. This V01 stands for V out 1. So this will be equal to 2R plus Rg. Now keeping my this thing here only and moving my this thing to that side, it is going to provide me V01 minus V02 will give me V1 minus V2 Rg plus 2R divided by Rg. So now dividing here, what we are going to get is V01 minus V02 will be equal to V1 minus V2 multiplied by 1 plus 2R upon Rg. So this is the output of my first stage. For a little bit, because we will be requiring it later, so I am just multiplying both sides with minus here. So multiplying minus on both sides will not make any difference, so that will make it to be V0 minus V01 and similarly V2 minus V1, while my this term will remain same, 2R upon Rg. So now moving on to my second stage, you have to remember your this output here because we are going to need it in our second stage. So now this is our complete instrumentation amplifier with 3 op-amps. This is the 2 op-amps of our first stage that we just discussed, and this is our third op-amp that is being used as a differential input, that is the differential amplifier. So here you can see that now we have got the output as this output will be equal to whatever is coming, because we have applied it at this negative terminal. So the gain will be Rf upon Ri into whatever is coming at the input, because this is in the differential mode. So that means the difference of these two will come, and the difference of these two will be equal to what we have applied at the positive terminal minus the negative terminal. And that is why we multiplied the previous equation with negative sign to get it in this form only, that is V02 minus V01. So now we have to apply the value here. So V0 will be equal to R0 upon Ri. Sorry, this is my R1. This is R1 here. So now this will be equal to V02 minus V01's value was coming out to be 1 plus 2R upon Rg multiplied by V2 minus V1. Now one thing that should be kept in mind is the ratio of R1 upon Rf should be made equal to the ratio of R2 upon R3. So for convenience, these resistors are taken in of the same value. Here a little bit of mistake has been made. So this is not R0 but Rf. Similarly here it is R0 but Rf. So I have just told you that for proper functioning of this, R1 upon Rf is made equal to R2 upon R3, or they are made equal. So if this is R1, this is also taken as R1. If this is the value of Rf, like 100 ohm, 2 ohm, whatever it is, so the same value is taken of this resistor as well. Now, if the value of Rf is made equal to the value of R1 again, then this V0 will be equal to, this will become equal to 1. So this will be equal to 1 plus 2R upon Rg multiplied by the input that we have applied at the first stage. So now this Rg, you can see, is inversely proportional to V0. That indicates that if we are going to increase the value of Rg, the value of V0 is going to get decreased, and if we are going to decrease the value of Rg, the value of V0 is going to get increased. So depending on the variations of Rg, we can get the output voltage according to our requirement. So if this thing is taken as A, this thing is taken as the gain A, then your this output will directly depend upon your V1 and V2 that you are directly getting from the transducers. That is your thermocouple, your piezoelectric transducer, your strain gauge, whatever you have applied, you can directly get your potentiometers. You can directly take the input at this stage, and then you are only going to get the output in your volts, because you have here applied in millivolts, still you will be getting in your volts, so that you can easily measure. So now we are going to come on to the various problems that you suffer from your operational amplifiers and how to solve them. So the various characteristics that we are going to discuss of your operational amplifier is first the offset voltage that can directly come in exam, that define offset retards with your instrumentation amplifier. Then comes the slew rate, common mode rejection ratio, and drift. So your operation, this instrumentation amplifier as a whole is important, and directly 5 marks numeric question can come on explanation of instrumentation amplifier and the various properties of operational amplifier, as well as the characteristic of operational amplifier, that we are going to discuss in our next lecture. So see you soon then.